So good afternoon, everyone. My name is Aman Dhakal. I'm working as a graduate research assistant at West Virginia University in the Pollution Prevention Lab. Today, I'm going to talk about a technology that contributes in solving two of the biggest concerns for any household, that is rising energy bills and the growing need for the climate action. For the decades, the way we heat our homes has relied heavily on the burning fossil fuels. In fact, using natural gas for the heating, which is a major source for the greenhouse gas emissions. This has created an urgent need for a better and cleaner alternative. The alternative is none other than heat pump. This is not just another appliance, it's a modern all-in-one solution that can provide both heating and cooling for our home. The US Department of Energy calls it as an energy efficient alternative to furnace and air conditioner for all climates. So over the next 20 minutes, we will explore this technology in detail. I will start with the brief introductions, then go over the types of heat pumps and how they work. And after that, we will examine the real world financial and environmental benefits of the heat pump. And after that, we will look at the current market trends and review some of the case studies and demonstrating real world savings and emissions reductions. So what are heat pumps? They are the innovative systems that use electricity to transfer heat. So what makes it so special? Heat pumps represent a fundamental shift in thinking. Instead of generating heat by burning something, they simply move existing heat from one place to another place. This is the major reason why heat pumps are super efficient than other furnaces. During the cooling season, heat pumps move heat from our house to the outdoors, and during the heating season, they move the heat from the cold outdoors into our warm house. Because they transfer heat rather than generating it, they can efficiently provide the comfortable temperatures for our home. So going through the types of the heat pumps, the first one is the air source heat pumps. These systems extract the heat from the outside here, even when the outdoor temperatures are extremely low. Then they transfer the heat indoors for the space heating and reverse the process for the cooling in the summer. Air source heat pumps are widely used in residential and light commercial buildings due to their relatively low installation cost and ease for the retrofit. Air source heat pumps have generally around 3 coefficient of performance. So in summary, air source heat pumps are practical and efficient option in moderate to cold climates, especially when combined with smart thermostat or backup systems. Next, we have geothermal heat pumps, which is also known as the ground source heat pumps. These systems extract the heat from the ground, which maintains a relatively constant temperature year-round, usually between 45 degrees Fahrenheit to 75 degrees Fahrenheit, depending upon the location. Ground source heat pumps circulate water or refrigerant through underground pipes, either in a horizontal or a vertical loop. So this allows them to deliver consistent performance regardless of outdoor air conditions. Because the ground temperature is more stable than air, ground source heat pumps tends to have higher coefficient of performance, often ranging from 3.5 to 5. This makes them one of the most efficient HVAC systems available. While the initial installation cost may be high due to some kind of excavation and drilling that needs to be done, the long-term energy savings and the low maintenance requirement can result in lower life cycle costs for the geothermal heat pumps. These systems are ideal for new buildings, schools, or facilities with available land area or access to borehole fields. So the third type is the absorption heat pump, which operates quite differently from other two. Unlike traditional heat pumps that use electrical compressors, absorption systems rely on a thermal energy source, such as natural gas, steam, solar heated water, or geothermal heated water to drive the heat transfer cycle. Instead of using mechanical compressions, they use a chemical absorption process, typically involving a refrigerant absorption pure like ammonia water or lithium bromide water. Absorption heat pumps are ideal for industrial or large commercial applications, especially where waste heat or non-electric energy sources are available. They are quite reliable and can be used in areas where electricity costs are high or grid infrastructure is limited. While less common, they play a valuable role in district energy systems, combined heat and power plants, and facilities with solar thermal integration. So let's move to the working of the heat pump. So how does a heat pump perform? The core concept is very much similar to like a refrigerator, but in reverse. The process is powered by what calls a vapor compression refrigeration cycle. In this process, the first process is evaporation, where the cold liquid refrigerant is pumped into the outer unit. Here, it absorbs the heat from the outside air. This heat, even from the air that feels cold to us, is enough to make the refrigerant evaporate and turn into a gas or evaporate. So after that, the next process is the compression process. In this process, the gas is flown to the compressor from the evaporator, which is the heart of the systems. The compressor squeezes the gas dramatically, increasing the pressure and the temperature, and leaving the gases at a very hot and high pressure. So after that, the condensation comes into play. The hot gases is then pumped to the indoor unit, and the fan blows our home's air over the coils containing the hot gas. The heat is then transferred from refrigerant to our air, warming our home. As the refrigerant loses its heat, it cools down and condenses back to the liquid. And finally, the expansion, where this high pressure liquid flows through an expansion valve. This valve causes a rapid drop in pressure, which makes the refrigerant extremely cold again, preparing it to go back outside and absorb more heat to repeat the same cycle. This key piece of technology allows a heat pump to provide both heating and cooling. Unlike a standard air conditioner, is a component called reversing valve. This valve simply changes the direction that the refrigerant flows, allowing the indoor and outdoor coils to swap and work on different climatic conditions. So, while choosing a heat pump, understanding its efficiency is a key, especially for heating performance. Let's break it down simply. Every residential heat pump sold in the United States has an energy guide label displaying its heating and cooling efficiency ratings. Heating seasonal performance factor measures the total heat provided over a heating season divided by the total electrical energy consumed. A higher value of HSPF is crucial for keeping heating costs down, especially in climates with the cold winters. In general, higher the value of heating season performance factor, the higher will be the cost of the unit. However, the energy savings can return the higher initial investment several times during the heat pump's life. A new central heat pump replacing a vintage unit will use much less energy sustainably, reducing the air conditioning and heating cost. So another performance factor is cooling efficiency. The seasonal energy efficiency ratio, it measures the heat removed over a cooling season divided by the total electrical energy consumed. The higher value of the SER, higher will be the cost of the unit. However, the energy savings can return the higher initial investment during its heat pump's life. Heat pumps generally achieve higher value of SER ratings, cooling efficiency than HSPF ratings. This is primarily due to the way heat pumps operate and how outdoor temperature affect their efficiency in heating versus cooling mode. The major factor for this is temperature difference. So let's look at the current heating technology used in the American homes. So among them, the first one is the forced air furnace. This typically have a burner in a furnace that is fueled by a natural gas. A blower forces cold air through a heat exchanger, which warms it up before it flows through the ducts that heat the home with air as the medium. And after that, second one is the heat pump. The most common type of the heat pumps, like air source heat pumps, which collect the hot air from outside of the home and concentrate it before pumping it through the ducts that heat the air inside. They are usually powered by the electricity. During warmer months, heat pumps can reverse themselves to cool the home, transferring hot air from the inside to the outdoors. So last one is the hot water stream. These systems typically work by boiling water or generating steam to the appropriate temperature using gas and sending it through a home's pipe to radiators that heat the air. So heat pumps are taking over the HVAC world, and for the good reasons. Let's look at the latest trends. The numbers says it all. Air source heat pumps are dominating the market with a percentage of 92.9% of installations, is they are versatile, efficient, and perfect for most climates. While others such as ground source heat pumps, which have around 1.5%, and water heaters, they are around 3.2%, are also in growing. In 2022, heat pump shipments surpassed gas furnace for the first time, capturing over 50% of the HVAC market. So why is that surge? The major reason might be energy efficiency is heat pumps operates in the lower cost than gas or oil, and another one is the consumer demand. So why heat pumps? Let's talk about the one of the biggest reasons to switch to a heat pump, which is the energy savings and ultimately the money. Because most of the heat is transferred rather than generated, heat pumps are far more efficient than conventional heating technologies such as boilers, heaters, and can be cheaper to run. The output of the energy in the form of heat is normally several times greater than the power required to heat the heat pump, normally in the form of electricity. A modern heat pump can cut our heating electricity use by up to 75% compared to old school electric furnace or baseboard heaters. It has other advantages such as it can lower the monthly bills, it is more efficient and comfortable year round, and it generates the less waste, which is also a greener policy. So heat pumps are also efficient because of their higher coefficient of performance. They deliver multiple units of heating or cooling for each unit of electricity. The chart shows the ground source heat pumps keeps a stable high COP since ground temperature stays fairly constant. Air source heat pumps may vary more because outdoor temperatures changes. When it's cooler outside, the old heat pumps must work harder and the COP may drops. In short, stable source temperatures means higher, steadier efficiency. COP values of heat pump typically range around 3 to 4, which is highly efficient for a heat pump. So, beyond just saving money, heat pumps makes a real difference for our planet as well. When we replace fossil fuel furnaces with heat pumps, we significantly reduce three key pollutants. First one is the nitrogen oxides, which is a major contributor to smog and respiratory illness. Heat pumps eliminates this at the source. Next one is the sulfur dioxide, which is known for causing the acid rains. This drops dramatically when you stop burning fossil fuels in the homes. And the last one is the carbon dioxide, which is the primary reason for the greenhouse emissions and global warming. The heat pumps can cut these emissions by 50 to 70% per household depending on our local energy mix. So after we know about the heat pump, there should be some criteria how to select and install the heat pumps. So the first one is the demand defrost control. This will minimize selecting a heat pump with a demand defrost control will minimize defrost cycle, thereby reducing the supplementary and heat pump energy use. And another is fans and compressors always makes noise. So we should locate the outdoor unit away from the windows and adjacent buildings and select a heat pump with a lower outdoor sound rating. We can also reduce noise by mounting the unit on a noise absorbing base. Also, the location of outdoor unit may affect its efficiency. Outdoor units should be protected from high winds, which can cause defrosting problems and may need to be elevated due to the snow buildup. So numbers tells the best stories. Let me show you how one of homes heat pump retrofit transferred their energy use and their utility bills. Before there was oversized gas electric furnace systems. Then after that it was upgraded to high efficiency slim duct heat pumps, which changed the heating season performance factor from 7 to 12.2 and changed the SCR ratings from 13 to 21. So the energy usage was reduced by 13,315 kilowatt hour per year. Efficiency was gained as home energy rating system HERS was dropped from 85 to 33. Also, the associated cost savings was around $1,600 per year. And here is the best part is our electricity grid shift to the cleaner resources such as wind and solar. Heat pump automatically gets cleaner every year, saving you money while shrinking our carbon footprint. So let's talk about one of the facility where an energy assessment was done by our P2 group at one of the warehouse. The warehouse was currently equipped with 12 large and 9 smaller low intensity tubular infrared natural gas heaters with an efficiency of 80%. The total output heat was around 855,000 BTU per hour and the input MMBTU was around 464.9. Given the area of interest, we recommended replacing the natural gas heaters with a system using 4 20-ton heat pumps with an associated equipment. The recommended system will provide 960,000 BTU per hour of heating output, which closely approximates the 855,000 output of the current systems. By switching to the heat pumps for the warehouse, it is estimated that these changes will vastly improve the energy efficiency due to the higher coefficient of performance and seasonal energy efficiency ratio of these modern systems compared to current equipment. This will result in reduced energy consumption and better climate control across all areas. The proposed energy usage is around 104.64 MMBTU, which will give around 360 MMBTU energy savings. So with the rate of 117 pounds per MMBTU, it will also save around 42,000 pounds of carbon dioxide emissions per year. So these are the references that I took to prepare my presentations. Thank you. And I will appreciate your feedback through the QR code.